And the lab manual should be look like this. The data sheet should be look like this. Excel sheet should have about 1, 2, 3 tables, and then little bit of a small. Those are not tables, just a place to do the percentage error analysis, and then there should be couple of graphs sheets, and then one place to place the figure. Okay, the screenshot. There should be about 3 graph sheets. Okay, so let's take a look what we're trying to do with this lab. We are trying to understand the Newton's second law behavior. So that's the plan. So this is a very simple lab. The theory part you should already came across in your theory class. So the Newton's second law, everybody know, if there's a force, mass times the acceleration, the one version of Newton's second law, mass times the acceleration should be equal to the force. You will talk about second version of Newton's second law later after you guys discuss the momentum conservation principle. Then the rate of change of momentum is actually the external force applied on the object. Okay. All right. So that's the plan. We're going to test this equation number 3. So if I want to test that equation, I want to have a setup. So our setup going to be look like this. If it is a general in-class experiment, this is the top of the table. You have object on the table which attach via a string to another object right here. You can see object number 2 can move vertical axis up and down, and the object M1 can move horizontal axis left or right. Okay. And if I set up the object like this and then let the object number 2 move downward direction, then object number 1 moves rightward direction. Since the both objects are connected to each other, acceleration of the whole system going to be the same, A. So you can apply F equal ma to object number 2, F equal ma to object number 1, and then build an equation, two equation with tension and the acceleration. And then you can solve those two equations to figure out the acceleration. Acceleration should be then m2g divided by m2 plus m1. So this the test is very simple. Now what we're going to do, we have a simulator which can simulate this exact principle. So what we're going to do, we're going to calculate the acceleration, because to calculate the acceleration, I just need masses of the object 1 and object 2 and the gravitational acceleration 9.81. So by doing that calculation, I can predict the acceleration. And after we done the simulator with the same masses, simulator will give you the acceleration. We can compare those two to understand whether our prediction is correct or not. If it is in class setting, that's a whole different scenario. We can't really get the acceleration directly. Instead, we have to do that by using linear equation. That's the step 1 of the experiment. Now, if I know the acceleration of the object, or if I can predict, or the simulator can give me the acceleration, then if I apply the same acceleration into the cart, okay, cart has a mass m1, and then if you apply F equal ma to cart, at this point there's no friction, okay, this is a frictionless surface, then you can actually find the relationship between the force acting on the cart, acceleration, and the mass, right? F equal ma, only one force, that is the tension, and the object mass is m1, acceleration a. So if I do this experiment by changing the M2, by changing M2 mean then we change in the force acting on the object number 1. If I repeat the experiment again and again for set of experiment for different mass M2, which mean technically what we're doing, increase in the mass M2, dragging power downward direction increases. So which mean force acting on the object 1 increases. So which mean the acceleration will increase. So if I have a set of data, I can make a graph, maybe if on the y-axis, acceleration on the x-axis. By looking at the graph, I can estimate mass of the cart. That is actually the main goal of the first part of the experiment. Question. Okay, let's continue into the simulator then. So the simulator is actually link you can find on page number 2, very bottom right here. Just click on that. Then you will get into a page like this one. One side is yellow color box, other side is orange, the green color box. And in the green color side, you should have a different option. The first, this knob is the reset knob and the start. And then you will see a mass of the wagon. Mass of the wagon is actually this blue icon right here on the top of this yellow horizontal plane. That is actually our mass M1, okay? Mass of the cart in our diagram right here, figure 1, okay? That's the wagon moving on the x-axis. And you can see that connected to the string, and the other side of the string you can see another blue small dot. So that is the mass M2, because since this is a frictionless situation, we don't need a lot of mass to drag actually this object downward direction. We need extremely small mass to drag the object, okay? And that mass is right here. It says a hanging mass on your green color box. And make sure coefficient of friction at this point 0. And inside this yellow color region, you can see an icon called LB. So what it does actually, it acts like a photo gate. So if I let the object run, for example, let's click this start to see what's going to happen. You can see object M2 moving downward direction, M1, the blue card, moving horizontally. So what this timer is actually telling you, always when you reset, this blue card goes to the always starting point right here, very left-hand side corner. That's the x-axis starting point 0, 0. After I start, what this LB is actually doing, it actually counting the time from starting point to that location. Right here in these red numbers in the middle, that tells you the time to car to travel from the starting location to the point of LB. If I reset this again, I can actually change the LB in between these two lines. Okay, this red point is the last point, and this point is the starting point. Okay, I can change it those location, but every time you reset, LB is automatically going back to the 0.5 meters. Okay, you can see 3 numbers here in the middle of the yellow color region. This S represents the separation between the front of the cart to the LB. Front of the cart is the X0 point, okay? And time is actually tells you, after we run the program, how much time the cart takes to reach the LB. And the acceleration I can calculate by using linear equation, right? So this has a constant acceleration A. I can use displacement is equal initial velocity T plus half AT squared. If you remember those equation, very beginning of the semester, you may came across by using that cart is starting with the initial velocity 0. So I can find the acceleration, which is going to be 2 times the displacement divided by T to the power 2. This one right here. So that will actually provide you the number, but we're going to calculate the same acceleration by using Newton principle. That is actually by using FA, not the linear dynamics, okay? A linear equation. So what we're going to do, we're going to compare those two. Technically, those two are going to be very closely matched because this is a simulated result. So our percentage error might be 0 or maybe very close to 0 at the end. So that's the part one objective. And the second objective is that testing the F equal limit. Then we're going to collect the set of data by changing the hanger mass. You can see table number 1, first column. As I change the hanger mass, acceleration going to be changed. We're going to calculate the force. Then we're going to make a graph between the force and the acceleration. Slope of that graph will provide the cart mass. That's the second objective of the part 1. Question. That's all. Then let's continue. Let's start from the table number 1. So the table number 1, we investigating the Newton principle, but without friction, okay? Friction make sure must be 0 right here. And the mass of the cart M1, we can set that into We can leave it 100. Don't need to change. Just that's the automatic number it's selecting. Just leave it 100 gram. I'm going to add one decimal place there. Otherwise, it's going to be like one significant figure. Okay, 100 gram, which mean about like 0.1000 kilogram. Okay. And distance to LB, that also fix. Starting point to the LB, that's going to be about 0.500 meters. Okay, right here. So that's going to be fixed throughout this part of the experiment. So what we're going to do, we're going to change the hanger mass in units of kilogram, and then check how the acceleration change, and then we'll collect the acceleration first and then calculate the acceleration again by using Newton laws. Okay. All right, so we're gonna start with maybe 1 grams. That's good enough. I think it's moving with the 1 gram. Or we can start maybe with the 2 grams. Let me take a look what's the suggested number to start with. We'll follow exactly tasking like 2 gram at a time. So we can start maybe 2 grams and then increase 2, 4, 6, 8, 10, 12. So let us start with the 2 gram. Doesn't matter actually, as far as objects are moving. 2 grams mean divide by 1000. That's going to be about 0.002 grams. Okay. 0.2 grams mean divide by 1000 into kilograms should be 0.002. If it's not visible here, what you have to do, you have to select the whole this data range, right click, format cells, numbers, and then it creates the decimal places at least to 3. Okay, then it will show up. And that's it. Then you click start button. Make sure hanger mass is 2, right? We're starting from 2. Hanger mass, click number 2 there, hit enter button. Mass of the wagon 100, mu should be 0. Everything else fine. LB is automatically usually set into 0.5. Just click start button and then wait until it complete. And then we extracting the time to reach the LB location about 2.280. And then we extract the acceleration. It says A given, that is the acceleration given by the simulator. That is 0.192. Unit of the time should be second. Unit of the acceleration should be meter per second squared. And then let's calculate the acceleration, calculate the force, and then check the percentage error between the expected calculated acceleration and the given value. Okay. Calculated acceleration unit always going to be meter per second squared. And you can calculate the acceleration by using the equation number 4 on your lab manual, page number 2. So that by using the Newton second law for the both objects, acceleration going to be then equal sign mass m2 times the gravity divided by m2 plus m1. Parentheses mass m2, which is the hanger mass. Don't write that number, just click on there because we're going to collect the set of data. Then the m2 going to be changing. Okay. And times 9.81. Parentheses divide by open parentheses m2, which is again the hanger mass, B number 12, plus m1 going to be fixed. It's not going to be changing at all. That is about 0.100 kilogram. Okay, 0.1 kilogram. Close brackets, hit enter. If my calculation is correct, then you should get exact number as your given acceleration by the simulator. You can see the numbers are extremely closer, extremely same. Because of that, what we're going to do, we're going to increase 1 decimal place on our calculated value. Since it is a calculated value, Let's highlight this column and then increase that, right click, format cell, increase the decimal place to 4 to see whether at least one number is different. Otherwise, doing percentage error is not much meaningful because you can easily see percentage error is 0. Okay. All right. And one important thing is still I see not many of you submitting the lab report, but I see almost everyone attending the class. So this class you will not be able to pass if you not submitting the lab report and then getting enough credit. Okay. This is a calculus based class. This is not like PHY 114 or 206 level. Okay. So the expectation on the standard of the class is much higher than those levels. If you're not submitting the lab report, you will fail this class. Doesn't matter you attend all the classes at all. I don't care, okay? You have to attend the class and also you have to submit the lab report. Lab report are not the data sheet. Most of the people submitting, but I see very few submitting only data sheet. Maybe they assuming they can automatically pass the class. That's a huge mistake. Okay. So please, if you have any question, please reach out and ask. Do not assume anything. Okay. So if you go into your grade book on the Blackboard page in our class, then you will, few of you will see zeros for all your previous lab report, which means you are very close to failing the class. Okay, and this is a lab class. I don't know why you really not submitting lab report because lab report is extremely simple. We're doing short lab report. We're calculating all the data here. You just need to copy paste this table one by one from here to Word file and then write a discussion. I have no idea how you're going to become engineer if you can't do that. So that's the bothering to me actually. If you have any question, please reach out and ask. Okay, that's a very funny situation for few of you. Now the other guys who submitting the lab report, nothing much to worry. Okay, that announcement only for few people. I know it seems to be they attending, but no submission. Okay. Any question so far up to this point? Fine. Okay, then let's continue. So what we have, we're gonna calculate the force, right? Force I can calculate by using F equal ma, right? So let's apply F equal ma to object number 1. Right now you can see object number 1 moving on the horizontal plane without any friction, which means there's only one force horizontally, that is the tension, right? So if I apply F equal ma, force I can easily calculate mass times the acceleration. Okay, question. Okay, so, and also hanger mass value is right here on the simulator. Right here, it's a hanging mass. That's the hanger mass. That's the one we're changing. Yeah, it's in the grams, so you have to divide by 1000 to get the right units kilogram. Okay. All right, so let's continue now. You can actually calculate the force by actually simplifying the Newton laws, right? Let's do that very quickly. Now, if I have a situation like this one, you have an object right here moving on a horizontal plane, and then there's a pulley. Other side, you have a hanger. This object is M2. This object is M1. Then you make a free body diagram. You have M1G downward direction, normal force up, tension force here, tension force up, M2G downward direction. Then if you let this go downward direction with acceleration, this will go horizontally with the same acceleration. Then let's write it down. I have two free body diagrams. Sum of all the forces is equal mass times acceleration. For object number 1, horizontally, then you will get the tension is equal m1 times the acceleration a. Then you apply the same vertically for the object number 2, then you will get T minus m2g, which is equal negative m2a. Then you can solve these two equations linearly to find it out, both acceleration and the tension. So if I subtract these two equations one from the other, T minus m2g is equal m1a minus m2a. T cancels out, minus minus positive, negative cancels out. You can take the a out, m1 plus m2. This side you will get m2g. So that's how we found that previous equation, right? Acceleration is equal simply m2g divided by m1 plus m2. That's the equation we just used to calculate acceleration. That's the equation you find it here, okay? And then if I want to find the force, I can use the same trick. I can either get rid of acceleration from the equation, or you can get this one and then plug it back into equation number 1, right? If you do that, you can find tension force is equal m1 times m2 times the gravity divided by m1 plus m2. That's the equation for the force. So instead of using the acceleration given, I can actually predict the possible force acting on the object number 1 by just knowing the mass of the objects, object number 1 and 2, and the gravity. So that's the way we're going to calculate tension force right here. Now you know the equation. All we have to do is use that to calculate the force. So I can use m1 times m2 times g divided by m1 plus m2, okay, equals, let me copy paste this function. You can collect all of these functions and then call them as needed in your discussion section. This is the acceleration cal function, and then we're going to do here the tension cal or the force cal equal sign parentheses m1 is 0.1 kilogram multiplied by m2 is changing. Click on this cell value B12 times 9.81 close brackets divide by open brackets m1.1 plus m2 cell value B number 12 close brackets, hit enter. So that's the expected force acting on the object number 1. This is force calculated. Question. Okay, so let's check the percentage error between the calculated and the given acceleration from the simulator. It's going to be, you can see almost 0, right? But let's do that calculation because that fourth decimal place is slightly different. Equal ABS parentheses expected value, we can say the theoretically expected value, that is the calculated value from our equation, right? Minus the given value divide by expected value is our calculated one, then multiply by the 100. Very, very small percentage error, about 0.1. This is the PE for ACE, okay, for acceleration. All of these functions you can use on the discussion section, or you can use that into the data section too. Under each table, you can show how you did the calculation, that also fine. Now, what we have is actually with the one hanger mass, and then I done the calculation, acceleration, force, and everything, right? So now what we trying to do, if I can get the series of data by changing the hanger mass, I can actually make a graph of force versus right here. If I change the M2 in this equation, right? If I change the M2 as a result of by changing M2, T will be changing. As a result of that, acceleration will be changing, right? So if you look at that equation, T is equal M1A. So if I have T, that's the force acting on the object M1, right? Cart. And then if I put that into y-axis, y is equal, this is going to be slope of the graph times the acceleration of the cart. So which means if I have a series of data, you can make a graph. X-axis is going to be acceleration, meter per second square. Y-axis is going to be the force. In your lab manual, just write it F, but I usually write T for the tension. That's why I did that. Otherwise, it's the same thing, okay? In unit Newton. And then you're going to get a data set something like this, right? So if I do the trend line, and then the slope of the trend line should be able to predict mass of the cart one. So that's the idea. So the mass of the cart one I can calculate by just knowing the slope of this graph. So that's the plan for this second part of this part, the second objective of this part. So as we collect the data, you will see the graph will appear, force versus acceleration. And then by using the slope of that, we can actually calculate the mass of the cart one. Okay, that's the plan. Question. Okay, then let's continue. All we have to do, increase the mass of the M2. You have to reset first, okay, before you do anything. Click the reset button on the top and change the hanger mass. That's the only one we need to change. Everything else you can keep it as it is. Hanger mass to 4. Click the start button, let it run. After it finish, put the hanger mass 004. Time to continue to that point 1.628, and the acceleration 0.377 from the simulator. They're actually doing this calculation. Okay, this part 2s over t squared, and the acceleration calculated, you can click and drag this previous cell number E to L. Then it will do it automatically. If I do the calculation correctly, I should get this answer. Okay. And also we can check this too. Let's check whether the calculation done by the simulator is by using this formula, right? That's why I wrote it down, the time here. Let's check that too. Previous one, equal sign twice. Displacement is actually about 0.5, and then divide by time to the power 2, right? So that means cell value C12 to the power 2. So I'm getting exactly the same answer. So there's no difference at all. You can click and drag and then check whether this number is changing. That is the number given. This is the number now I calculated with this equation. It's exactly the same one program is doing, okay, internally. That's why when you use the simulations, almost we get in the perfect answers, because internally the program does the calculation anyway. Okay, question. Now, actually, you can do this acceleration also this way if you want to. Otherwise, just write it down, the given number directly there, nothing wrong. This is actually a given, but I can do that calculation to check whether that's the right one, okay? All right. Question? Okay, then the force calculated, you can click and drag. And also the PE, you can click and drag, because since we use the cell values, those things will be calculated automatically. You just need to do for the first line. And also the graph should appear. I see the axis actually flip on the graph, but I will check that in a bit. Okay, just leave it like that. Question. Okay, then let's continue. All we need to do, just click on the reset, increase the hanger mass to 6 grams, and then let it run. 0.006, and then the time is about 1.342, and then all the rest we do the calculation instead of bringing the number their acceleration. Let's click this and drag, and then check whether I'm getting the exact number. See that I did the calculation 0.555. That's the same number given there. And in all these, you can just click and drag the cell. That will do the calculation automatically. The graph should appear as you do the calculation, okay? See that linear graph, which we expecting right here, force versus acceleration. That's all. Then reset again, change this into 8 grams, let it run. After it finished, now it is 0.008. Time is about 1.173. And all of these you can click and drag. That will do the calculation automatically. And check the acceleration, okay? My calculated value and the value showing here on this yellow area, that two should be matched. PE, I don't know. You can check the formula. If the formula is wrong, anything wrong in your equation, then that might will give you different answer. That might be a problem. You need to check the formula, okay? If your formula is correct, there's no reason to be this number is different at all. That's very weird. That's okay. We can take a look at the end. As far as if it is a small number, it's not big deal. Small numbers, right? Okay. We can take a look at the end. Let me take a look very quickly whether that's the problem. Okay, I know what the problem is, because it's not reading this number correctly, because it's a calculated value, I think. Let me check that. E12, why it's not reading correctly? It should read. Yeah, you guys are writing the numbers directly from the acceleration values directly from the simulator. I doing the calculation here. That's why, due to some reason, it's not reading that correctly. That's okay. Just leave it there. I can take a look at that. As far as less than 0.1, that's okay. That's fine. So let's continue. This is we need 2 more data points. Reset again. Change this into 10 gram. Start. And we need, now we are 10 gram 0.010, right? 10 gram time is about now 1.059. And then acceleration 0.892, that's my calculated one, but that is exactly the same as this given, okay? And the rest is automatically will calculate. Reset, 12 grams, start again. And we have 0.012, and the time is about now 0.0975. 0.975. Then your acceleration is 1.051, and acceleration cal is almost the same. Okay. This PE value, just leave it. We can take a look at the end, but why it is not reading it correctly. Let's take a look at the graph now. So now the graph should appear very linear, acceleration versus force. I need to take a look at these two numbers because I want force on y-axis, right? Because our equation y equal ma, force should be on y, acceleration should be on x, right? Let's take a look at that two numbers very quickly. I mix the, you can take a look very quickly if you do this. Let me show you. Double click on the graph and then click on the date, select data, right hand side very top. Then click on the series right here and then click on edit. Then if you click on the X values, that will highlight the data range. Okay, now you can see I mistakenly put the normal for the force onto X-axis. Doesn't matter actually, still we can do the graph as it is, do the calculation. Let me show you that too. Just leave the graph as it is. But that will be slightly different now, right? So instead of this graph, we have actually now graph look like this. Acceleration is equal 1 over mass m1 times the force. So now this is on y-axis, this is on x-axis. Then the slope of the graph right here gonna be 1 over n. Slope of the graph gonna be 1 over m1. So the m1 gonna be 1 over slope. We can do that way too, okay? If you want to keep it like that, you can do that way. But to follow the lab manual exactly, we'll change this axis, okay? We'll flip the axis. Double click on the graph number 1, figure number 2, select data on right hand side top. Click on the series, click on the edit. Then you can see x-axis values here, delete everything there. And the x values, I need acceleration right here, acceleration calculated values. Okay, click and drag the range of data from E12 to E17. Then delete everything on Y, and then Y value should be the force. Click and drag F12 to F17. Click OK, click OK again. Now I have the right graph, but I have to flip this axis, which means I have to rename this, okay? Click any of on just top of this name right here, x-axis title, and then you can delete there and then retype the right term. This should be acceleration. Unit should be meter per second squared. And the y also, just click on there, just delete everything there. And now that should be force. And unit should be Newton. Now we have the right way, the acceleration, what the lab manual want us to do, okay? If you don't want to change that, make sure you rearrange the formula on this way. Then the mass going to be 1 over slope. Okay, do not miscalculate that. If your axis is flipped, mass should be 1 over slope. If you correct the axis this way, then mass going to be directly the slope. Let's check that. Now to check that, I need to see the equation of this trend line, right? Bring the mouse cursor on top of the trend line anywhere, double click, right hand side very top, third icon, trend option, go all the way to the bottom, click all of these 3 options. Then you should see equation show up. On that equation, number in front of the x should be now the mass of the cart. Okay, mass of the cart is 0.100 kilogram. That's what exactly we're getting, 0.1. Okay. And we can increase actually decimal places too here. If you double click on this, you can see this equation is actually around that small line. If you click there, right, a small black line, dotted line. If you double click on that dotted line, then on right hand side, a window will appear. Fourth icon of that. If you click on the fourth icon, last icon, then it says number and category. All you have to do, go in there and then click on the number, change the decimal place to about like 4 to make sure that actually 100, because if I have a second decimal change, then the error going to be so high still, right? I need to make sure that exactly the number we're looking in. So it's better if we have a more decimal place there to make sure the number is correct. Okay, so question. All right, so then let's continue. So we done first part, and also let's bring the picture to here. Since we're doing only short lab report now, everything right here on the data tables and the pictures and everything must go to the data section, okay, on your report. Yeah, so all you have to do, just bring the cursor on top of this equation. Then you will see a line appear on around it. Just bring the cursor top of the line, then double click. Then on right hand side, there's a 4 different icon on the top. Click the fourth one. Then you will see this category. Inside that, select the number. Then you put here number 4. Then we can get 4 decimal places. Let's take a screenshot. And that is screenshot, we can put it here, insert, illustration, pictures, and then bring the screenshot that usually go into the pictures folder, right? Right there. And make sure getting rid of any of the unnecessary information and then leave only this area. That's the only part we would like to have there. Okay, that's our picture. Okay, question. All right, then let's continue. So the analysis of the cart of the mass, slope of the graph is 0.100 kilogram. Mass of the cart from the gram is actually that one. Slope is the mass, 0.100 kilogram. There's no even meaning doing error calculation here because you can see the two numbers are exactly the same. There's not even meaning doing it. We can just say 0. No even meaning writing the formula. Okay, question. Okay, then let's continue to the second part. Second part is also same, only what we're going to do here, we're going to apply the friction and then let's check, let's see what's going to change, right? So let's apply the friction here. Let's see what's going to change. Now, yep. Okay, good. All right, so let's apply the friction. Then let's take a look the free body diagram again. I have a cart here connected to a string, and then other side I have a hanger. This side free body diagram M2G, and then tension T, moving downward with acceleration A. I have a tension T. Vertical axis you have M1G and the normal force. Now we're going to consider the friction, right? So the friction is always opposite to the motion, right? So now let's do the same thing again, which we done. So you can apply F equal ma, sum of all the forces is equal mass times acceleration for both objects. If I apply to M1 now, the things will slightly change than the previous, right? Positive direction I have T, negative direction I have F is equal mass M1 times acceleration. Whenever you see the friction force, by now you know friction force is equal friction coefficient times the normal force. And to find the normal force, you look at the y-axis direction on mass M1. Then you can see normal force minus M1G is equal 0. Normal force equals simply M1 times the G. So if I put all of these information together, you have one equation T minus mu times M1G is equal M1A. Now that is the equation number 1. So that's different than the previous. If you look at the object number 2, M2, y-axis direction, you have T minus M2G is equal just simply M2 times A negative direction. That equation number 2. So again, it's the same thing what we done earlier. You have two linear equations. You solve them linearly, right? If you add them together or subtract them together, you can get rid of t. Mu m1g is equal m1a. T minus m2g is equal minus m2a. Let's subtract these two together. T cancels out. Negative mu m1a plus m2g is equal m1 plus m2 times acceleration. Then I can find the acceleration. It's going to be g. I can take it out. Then I have m2 minus mu times m1 divided by m1 plus m2. Now that's the equation for acceleration. Now that's slightly changed than previously. Okay, not much. See the previous equation right here. That's the previous equation, right? m2g is there, m1 plus m2 there. Only difference is now is this part. The new components show up because of the friction, right? You can see that's minus. So which means the friction is actually reducing the energy from the system. So the acceleration now going to be less than the previous, what we calculated. Since I know the acceleration, you can take that and then plug it back into any equation. You can find the tension, right? Or the force. Or you can solve these two again. T minus mu m1g is equal m1 times A, and then T minus m2g is equal negative m2A. If I want to solve this, I will just get rid of A, actually that much easier. T over m1 minus mu g. From this equation you can find A T over negative m2 negative plus times g. Now you can see you can get rid of A. I just show you this one because this is a very standard question which may be very useful for your lecture class if you take in that class simultaneously. I don't know which place you are in, and then I don't know how much information that the exam is asking. If that exam is asking up to the level of the calculus class, then you should be able to do this way in like within 5 minutes of the time. Okay. So if you subtract these two or equal these two together, you can find the t. T over m1 minus mu g is equal t over negative m2 plus g. Bring t's into the one side, then you can have the answer. 1 over m1 plus 1 over m2 is equal g times 1 plus mu. Then your t is equal m1 plus m2 times 1 plus mu times gravity over m1 plus m2. That's a very nice equation. If you take a look that and the previously what we got right here, see that? Whenever mu is 0, I can go back to the same, right? You apply mu equals 0, you can go back to the previous equation. You apply mu equals 0 here, you can go back to the previous. So it should be consistent with everything we're doing, okay? So now that's the plan for next part. It's not anything new, nothing much really. We just going to do the same experiment applying mu, and then we're going to use these two equations to reach A. There's nothing new at all. Question? Okay, then let's do that. So all we're going to do, we're going to apply a little bit of friction and then repeat the experiment. That's all right. So we can keep the cart mass same, 100 grams mean 0.100 kilogram, right? And then LB, you can keep it there, 0.500 meters, nothing to change that. But now the friction coefficient must apply. So let's take a look what number the lab manual is suggesting. We can apply technically any, doesn't matter. But if we apply really large friction, maybe we might not able to move that at all. So it's suggesting you to apply about extremely small friction, 0.01. So that may be important because if you apply large friction, this will not be able to move at all. You remember, hanger mass is extremely small, okay, about 2 grams. So if I apply large friction here, system will not move at all, okay. preset. Let's apply this about 0.01, right? Now the friction coefficient should be 0.01. You have to record that into here because we need that for calculation too. And hanger mass in kilogram. And the time, we even don't need actually time. I put it there because we can calculate the acceleration. Since we already have seen this equation, we check that. We don't even need that, but let's complete that since it is on the table. Acceleration given meter per second is squared. You can get that answer directly from the simulator. Acceleration calculated. Meter per second is squared. That you have to do now by using our new formula, okay? That also given on, if you take a look, that equation already on here, right? That's the equation, and also that equation you can find on your lab manual, right here, okay? And force we're going to calculate by using that equation. Unit Newton, we're going to check the acceleration percentage error. Same may be done earlier. Okay, then let's continue. We're going to start with again 0.2 mass, right? And if there's no enough significant figures, you may have to highlight the whole area and then increase the decimal places into at least about 3, okay? Highlight the whole data set, right click, format cells, numbers, decimal place to about 3. Then it will show you enough enough decimal places, okay? All right, then, I mean, that's it. We just repeating the same thing. We're gonna go back to 2 gram. Bag and mass, keep it same. Now we have very small friction there. And let us start. You can also check with the higher friction. For example, let's say friction is about 0.1. Let's say whether this is running. See, it's saying too much friction. See that?
Professor?
So the system will not run. Yeah.
Isn't it 0.002? You put 0.2.
Oh yeah, this one 0.002, correct. Mass should be 0.002, right? 2 grams divided by 1000, correct. See, I check with the 0.1 gram of 0.1 of friction. You can see it says too much friction. So because the hanger mass is extremely small, okay. So that's why we have to go really low friction here. All right, so that's it. Then let's start it and then let it run and then collect the information what we want, the time even we don't need, but let's collect it. Now you can see the time is much larger compared to the previous, right? It is actually taking about like 3.225. Acceleration you can calculate 2s over t squared, but you can write it down directly. Acceleration, this number now must be less than the previous. You can check that, okay? Earlier time is 2.2, acceleration is 0.192, moving faster, time is less. Now acceleration is lower, moving slower, time is high. Let's calculate the acceleration then equal sign by using our equation, right? Our equation acceleration, we got g times m2 minus mu m1 divided by m1 plus m2. Let's do that calculation. Equal sign, parentheses 9.81 multiplied by another parentheses m2. Why it giving me sheet 1? Because I click earlier on the other sheet, that's why. Okay, m2 is this cell number B38, cell number B38 minus parentheses mu is 0.01 multiplied by m1, which is about 0.100, right? 0.1. Close bracket, close brackets again, close brackets again. divide by parentheses M1 is 0.1 plus M2 is 0.002. It always give me this sheet number because I think I earlier click on that the other sheet. That's why, okay. You should not see that error at all. And then hit enter. If my equation is correct, I should get exact answer as we getting earlier. Okay. Let me copy paste that function here. This is acal. Okay, and also like earlier case, you see it's two perfect, percentage error is 0. We can just highlight this column E on table 2, and then right click. Maybe you can change decimal places, format cells, increase decimal places to 4 to see whether I'm getting at least a little bit different number. Now we have very small difference on about like 4th decimal place. Okay, let's calculate the force 2 equation for the force. If you remember earlier, M1 M2 parentheses 1 plus mu times G over M1 plus M2, right? So let's do that equation. Equal sign, M1 is 0.1 multiplied by M2 is B number 38 multiplied by 1 plus mu, right? Mu is 0.01 parentheses 1 plus mu 0.01 times 9.81 divide by parentheses M1 is 0.1 plus M2, click on the cell B38, close brackets, hit enter. Let's copy paste that function 2 into here. That's the force cal, okay. Okay, equation. Okay, then that's all. Then all we're gonna do the same trick like we done earlier. Let's continue. Percentage error again we can do like we done earlier to compare a acceleration to values, right? Equal sign ABS parentheses calculated acceleration minus experimental value divide by the calculated value multiplied by 100. Gonna be should be very small number. That's gonna be the PE. And all we have to do now, same thing, repeat by increasing hanger mass. That's all. Just reset and increase the hanger mass to 4 grams. Repeat the experiment. The friction coefficient remaining as it is. Okay. Wagon mass remaining as it is. LB remaining where it is. Start. Let it run. Collect the data. Now we are on 0.004. Time is 1.880. And the acceleration now, which is about 0.283. Acceleration calculated, I can click and drag this. Almost the same. Force I can click and drag. Percentage error also we can click and drag. And that's all. Just you reset, increase the hanger mass into 6. Repeat it like we done earlier. 0.006 time 1.470. And the acceleration 0.463. You can see with the hanger mass now acceleration increases by large. Okay, And the last 3 columns you can just click and drag because we just did the calculation. It should give you the right answer. Next, 0.008 of hanger mass, reset. 8 gram of hanger mass, start. Time 1.254. And the acceleration 0.636. And these 3 values, you can even click them together. It will do the calculation still correctly. You can always check the acceleration 2 values. That's the best way to compare, right? Then we know our calculation is correct. Next, hanger mass 0.01. Reset. Hanger mass to 10 gram. Start. Time is 1.116. Acceleration 0.823. These you can click and drag together. It will do the calculation for you. Last hanger mass 0.012, 12 grams, right? Reset 12 gram of hanger mass, start again. And then the time is 1.019, acceleration 0.963. Question. Now again, if you take a look the graph, I need the graph, again the same thing, okay, same graph, I need force versus acceleration, but I think my graph when I set it that, you can see the axes are flipped. Let's correct that first. Double click on the graph sheet anywhere. Okay, good. Double click graph on anywhere. And then click on select data. We need the force versus acceleration, right? Series 1. Click on edit. Then delete everything on X. And the next should be now calculated acceleration here. And then Y should be calculated force here. Okay. Calculated acceleration column is E number 38 to 43. Calculated force going to be F number 38 to 43. Then click OK. Click OK again. Now axes are corrected, but still I want to change this name, right? Now this should be acceleration x-axis. Please correct that, okay? Acceleration, unit meter per second squared. And the y-axis should be now force. And the unit should be Newton. Now again, we can take a look the equation of the trend line, right? Now you can see trend line is shifted, right? See earlier trend line passing through exactly 0, 0 point. Now the trend line you can easily identify is shifted. So why it is shifted? You take a look the formula, right? So if you take a look the formula, what equation we are working on, this equation number 1, this equation, right? If you take a look that equation, how it look like? I have T minus mu m1g is equal m1 of A. Now, if I rearrange this into T is equal mu1 A plus, sorry, m1 A plus mu times m1g. Now you can see what we actually making the equation look like. I'm making this is into y-axis and then acceleration into x-axis. Now this look like A is equal AX plus B. So that's the idea. Now your equation should show you this y-intercept, right? See that? So technically the slope is still show you the M1, but by using the intercept, if I want, for example, I can re-estimate the friction, for example, let's say if I don't know, or if I know friction, I even can calculate the gravitational acceleration. We can do a lot of other calculation and analysis by looking at that graph, okay? So that's why it has intercept. See that it passing through now a little bit higher on the y-axis. Let's show the equation. Bring the cursor on the trend line, double click. Linear is fine, but when you click the last icons, only click last two. Do not click the set intercept, okay? If you click that, this will give you a completely wrong answer, okay? Don't click that at all. And if you want, you can extrapolate this backward to see where it's crossing. You can see that if you put about 0.1 into backward location right here, hit enter, you can see that is actually crossing exactly around here. That's the intercept on our equation. This equation, y-intercept mu times m1g. Question. Okay, again, bring the cursor onto this equation. Then around you will see a line. Just double click on the line and then go to the last icon on the very top, right side, last icon, category, change into numbers, change the decimal place into 4. Then you will see a little bit of larger decimal places here because I want to make sure the slope what we're getting exactly 0.100. If it is even 1 decimal place change, there are going to be a lot of percent error. Okay, so we are good. It's 0.100 like the previous case. Question. Analysis from the slope of the graph 0.100, and we know mass is going to be exactly the same, 0.100 kilogram, and the percentage error going to be 0 because of that, right? 0.100 kilogram the slope. We don't need to even do that calculation. It's perfect number. Question. Okay, so the last part of the lab is actually not Newtonian, not Newton laws, but we're going to check the acceleration by using this given information. Okay, that's the plan. So basically, we are actually testing that linear equation, right? Remember earlier we mentioned one of the linear equation we are using here is actually this. You came across this very beginning of your semester, I think. Also, we used this equation earlier in few experiments. So you can write 3 linear equation, right? Displacement x or y, which is equal initial times the time plus half acceleration t, right? So that's the equation we're testing. In this case, displacement we're writing as S or D. V0 is actually 0 because of that part is 0 plus half acceleration times t to the 2. Now acceleration I can calculate from here. Acceleration is equal to twice s over t to the power 2. Or if I have this as an equation, s is equal a by 2 t to the power 2, I can put this is to y-axis, this whole thing t is equal to x-axis. Then the slope of the graph, let's put here different letter, maybe c. Slope of the graph should be acceleration divided by 2. Right? So which means the acceleration I can find 2 times slope of the graph. That's the plan. So we can easily do that if I have a set of data. That's the idea. Question. That part is nothing to do with the Newton's second law. So what we need is we're going to go back to reset the simulator. Hanger mass actually doesn't matter. You can leave it into 2 because we're going to go back into 0 friction. Okay, make sure it's 0 friction. Mass of the card doesn't matter. This is only for reference purposes. 0.100 kilogram. Hanger mass doesn't matter, but let's put it 0.002 kilogram. That's only reference purposes. And acceleration given going to be depending on these two numbers that will show up there. That will be constant throughout the experiment. We're not going to changing any of the masses, okay? What we're going to do change is the displacement between the cart frontage to the LB. You remember I mentioned LB, I can click and drag. So let's bring all the way to this about 0.1 place. Location of about 0.1 away from the cart. You can see now SC is 0.100. Displacement measured in unit meters. Time gonna be measured in unit second. And also I need time square to make the graph. This is gonna be s to the power 2. Let's start the displacement about 0.1 meter, okay? So I can add actually one decimal place you see there, right? If you want to do that, what you have to do, click and select this all range of data, right click, format cells, change numbers here in the decimal into 3, okay? We can show the amount of decimal place, significant figures we are observing in the simulator. We would like to report all the numbers we're reading, right? So that's why. All we need is the time to reach that point on the LB. So all you have to do, make sure wagon mass 100 grams, hanger mass 2 grams, friction coefficient now 0, okay? Click start. Then all you have to write it down is the time in this case 1.02, okay? And all we're gonna do reset. Every time you reset, LB goes back to 0.5. Now what we're gonna do, we're gonna change the LB, location of LB every 0.1, right? Earlier I did 0.1. Now let's bring this back into 0.2. We'll increase at a time 0.1. That's all really, and then we start again. Displacement now 0.2, time it took 1.442. And then you repeat at a time 0.1, next data point gonna be 0.3, reset, click and back into 0.3, start. Time is about 1.766. You can see even this the same acceleration, but the displacement I'm counting is larger, so the time should be slowly increasing, right? Next point should be then reset about 0.4 and start. Any question? 2.039. Any question? Reset. 0.5 gonna be fine because that's a reset point, right? I don't need to click and drag, that's already there. Just you can click start. And the time is about 2.280. Reset 0.6. Now you have to click to the right hand direction, okay? Start. 0.6 displacement, time is 2.498. Next one is 0.7. Reset. Click the LB and then drag to the rightward direction. Now I need 0.70. If you don't see the number immediately, you may have to click drag up and down, you know, left and right little bit. Then you can exactly pinpoint that location. You can see you have to click and drag very slowly, then you will find that number exactly, okay? Click start and then wait until run. So the time is about 2.698. And next point is 0.8. Reset. 0.8. Start. And the timer is 2.884. And the last data point we need 0.9. Reset. LV should be at 0.9 meters away from the cart starting point, right? Click start. After it run, timer is 3.059. Okay, so the data is done. All we need is actually this this graph, right? To make that graph, I need x to be t square, right? So which means we're going to make the graph x to be t square, second to the power 2, y to be the displacement in unit meters, then you will get a linear graph. Slope of the graph can be used to find the acceleration. That's the plan, okay? So let's do that. T square going to be equal sign time, cell number C61, power is shift and number 6, number 2, power 2. So that's only one command you may need for this one. This is going to be T to the power 2, calculated with that command. And just click and drag, that's all really. If you click and drag, it will do the calculation automatically. As soon as you have it, then you will get the graph. Let me check that axis 2, whether we have it correctly or not. Axis x should be time is squared, numbers are fine. And y should be displacement, numbers are fine from 0 to 1. Yeah, this is good, nothing to change. And again, I need the slope of the graph, right? Just bring the cursor on the top of the trend line, double click. Then in this graph, intercept should be 0. You can click all these 3 icons, okay? Intercept must be 0 for this one. And then what we're going to check at the very end now, slope of the graph, number in front of the x, 0.0962. That's the number in front of the graph, okay? 0.0962. Unit should be meter per second squared because that must be the slope of the graph, okay? Unit should be meter per second squared. But to get the slope, what we have to do, we have to multiply that number by 2, right? You see that? Slope multiplied by 2 is the slope, is the acceleration. So let's multiply this number by 2 equals sign 0.2 times 0.0962. So please increase the number of decimal places on this also because it rounded to 2 looks not good. So increase that into about, right click, format cell, decimal places at least 2, 4, okay? Use at least 4 decimal places. Unit, you can write it down here, slope of the graph here or here, okay? Doesn't matter where the unit is, but unit should not be on that line. You can put it in here, that's easy. And the slope of the graph also have the unit the same, okay? Meter per second squared. Okay, question. Let's check this with the PE. PE mean actually, if you go back to the simulator tell you the acceleration, right? See that? 0.192. So that's the expected one. So let's compare with that. So the expected one is 0.192. I have 1924. Let's compare it here. Equal sign, ABS, parentheses, expected 192 from the simulator, 0.192 minus calculated is 0.1924, close bracket, divide 0.192 multiplied by 100. So I have about very small percentage error, but it's better to check that anyway. So this is the PE equation here. For this part of the calculation, PE. And also here I did the slope calculation, the acceleration calculation by using the slope ACAL, A from the graph. That's the A from the graph by using slope of the graph, okay? Okay, and there's no post-lab question for this lab, okay? You see that term here because most of the time, a lot of you asking that question. So there's no post-lab question, and then 2 graphs, and then 1 simulator picture, 3 graphs, 1 simulator picture, and then 3 main tables, and then there's a little bit of small tables like this. These should go under the graph, right? Under each graph, you have to put that calculation related to that graph, okay? You have to show that. And then that's it, I think. You can stop here. If you have any question, stay on the call. We can take a look at that. Otherwise, I will see you guys on next week. Please submit the report, okay? This is only if you're not submitting. Please reach out and ask any question, because if you did not submit the report, I can't do anything. I have to work only with the syllabus document, right? So your grade gonna be lower. So that's not good idea. Okay, see you then next week.
Thank you, Professor. Have a good night.